Welcome. Today we will be looking at the notes worksheet entitled Sequences Day 1. And this lesson is an introduction to our unit dealing with algebraic patterns. We will be focusing most of our attention on two particular types of algebraic patterns, but these two notes worksheets, Day 1 and Day 2, sort of just represent a foundational piece, representing numerical patterns algebraically. So what we'll do today is just kind of start out with an introduction, and we're going to look at what is called Pascal's triangle, named after Blaise Pascal, who gets most of the credit for this, although it has been found that he was not the first mathematician to do work with this triangular array of numbers. So we're actually going to see Pascal's triangle a couple different times over the course of the next several weeks. So this just offers me a way to go ahead and introduce it, and so in the future we can kind of run with it in the contexts that we will see it in. But for right now, just what we'll do is try to peruse some algebraic patterns in it. So anyway, guys, if you would, at the top, can you just go ahead and give me a 1? And as I mentioned, this is what is called a triangular array of numbers. So what we're going to do here is start with the 1 and then work outward from there. The 1s will always be on the outskirts of each row. And so we're going to do a 1, and then a 1 and a 1, and then everybody, if you would, a 1 here and then a 1 here. And in between any two numbers, the way the value is given is the sum of the two above it. So the 1 and the 1 there make the 2. And so that would be our next row right there. And then keep starting out here. You'll see a lot of symmetry. And these values do have some meaning in some of the math that we're going to see before the end of the year. So anyway, let's go ahead and put the 1, 3, 3, 1. And let's just keep going there. I'm going to do a few more rows. If you can go ahead and follow my lead there, you probably do it quicker than I'm going to do it up here. That would be the next row. And you could see our nice triangular array forming here. And then how about a 1, 5, 10, 10, 5, and 1. Looks good. And let's see, 1, 6, 15. How about a 20 here? 15, and a 6 and a 1. Again, notice the nice symmetry there. And what the heck, I'll do one more. How about a 1, 7, 21, 35, 35, 21, and 7, 1. Nice. And as you can see, this triangular array is made up of a variety of rows. So the horizontal pieces, we'll kind of focus on that. And by the way, just you'll see sort of why this occurs as we introduce it again and again before the end of the year. But Pascal's triangle actually starts at row 0. So if you get an opportunity, you can go ahead and put a little row 0 right up there. This would be row 1. This would be row 2. And row 3. And again, there are certainly reasons for that. For right now, you can just kind of see, well, okay, the 3s are there, so it's sort of a benefit to have that as row 3. But there is another reason that it does start at row 0. And we'll talk about that when we see this again. So anyway, this would be row 4, and I'm just going to dot, dot, dot this kind of on down that way. And as you can see, it has rows, and it also has diagonals. You can kind of go either direction on this, but this would be diagonal 0. This would be diagonal 1, this would be diagonal 2, diagonal 3, etc., right down the line. Okay, great. So you know what you can do is just kind of put a dot, dot, dot on this, just kind of looking at my triangle. Obviously that goes on indefinitely. And I figured what we would do is just track a couple numerical patterns there and maybe see if we can represent them algebraically. We'll just kind of have to see how it goes. So anyway, let's go for it. Just as I said, an introduction to numerical patterns and a way for us to represent them mathematically. So here's what I have. One of the interesting patterns here deals with what's called the sum of the numbers in a row. And so as I said, that top row is row 0. Next one is row 1, row 2, row 3, row 4, row 5. And what I'd like for us to do is find the sum of the numbers in each of these rows and then see if we can come up with an algebraic expression for the sum in any particular row, the nth row. And so let's go ahead and take a peek here. I'm going to have to go back and forth on mine. You can just take a look up above. So here's row 0, everybody, straight across. And I hope everybody sees that the sum would be 1. Here's row 1. Sum of those numbers, everybody, is 2. Here's row 2. 1, 2, and 1. The sum of those numbers is 4. Next one, row 3. The sum of these numbers is 1, 3, 3, and 1. and that would be 8. And so we'll continue here, and I'll add to my table. But from what I saw, everybody, the sum in row 0 is 1. The sum in row 1 is 2. This one turned out to be 4, if I remember correctly. The sum of the numbers in row 3 turned out to be 8. If you look above, and I'm not going to go back a screen, but if you look above and you add all the numbers in row 4, you get 16 and 32, etc., etc. And then, everybody, what I'm looking for now is, could you tell me the sum for any row number, the nth row? So if I asked you to come up with the sum of the numbers in row 100, well, without writing row 100 down, so what we're looking for here is then an algebraic expression for the sum of the numbers in the nth row. And so what you're doing is looking for a rule, an algebraic rule. How do I get from this to this, this to this, this to this, etc., etc. Kind of a rule for the inputs to create the outputs. And potentially you've written this on your paper already, but it looks like all of those are powers of 2. And so it looks like 2 to the 0, 2 to the first, 2 to the second, 2 to the third, and so forth. So if I asked you for the sum of the numbers in row 100, rather than writing them all out and adding them all up, well, based on this pattern, you see it should be just 2 to the 100th. Excellent. Just maybe one or two others here that we'll take a quick peek at, and this one might be a little difficult for us. What are called the triangular numbers, and I'll go ahead and show those to you here in just a sec. So the triangular numbers actually pop up in Pascal's triangle along one of the diagonals. And I'll just go this way if that's all right with you. 1 happens to be a triangular number, and I'll describe what that means in just a second. 3 is a triangular number. 6 is a triangular number. 10 is a triangular number. 15, 21, 28, etc. there. So this diagonal right here gives us our set of what are called triangular numbers. So let's fill those in first, and then of course I'll describe. And in this case, I'll just sort of do it as our first term, second term, third term, etc., there. So I think I said 1, then 3, then 6, 10, 15, 21, etc., there. And by the way, again, just to sort of give you a heads up as to why those are called triangular numbers, it's because if we were to kind of see them geometrically, we could write them as in terms of triangles. So there's your 3 right there. This one is what it is, but you could really see it on the 3 and the 6. So representation geometrically of that value as a triangle. And 10, of course, would be the same. And you can kind of see what's going on with this pattern. If I asked you maybe what the next one would be, you could probably come up with it, and then the next and the next. But the key is, could you tell me an algebraic rule to find it? So what would be the nth value? And so you're going to have to stare at that one for a little bit here. This one's a little hard, but let's see. So I'll give you a hint, and actually I might leave this blank. I'm just kind of thinking about what's on the back side there. And we might have to revisit this one. I might let this one hang for a little while and then come back to it a little later on. So anyway, I'll give you one hint though. What you have to do is use 2 different inputs to come up with each output. So it's not necessarily what do I do to 1 to get to 1, although that is part of it. But think of this to get that. Think of this to get that. Think of this to get that. And etc., etc. Sorry, just trying to give you visual cues on this one because this one's quite hard and it doesn't come just naturally there. As I said, I think if I remember correctly, it's on the back of your notes worksheet as well. So I might leave this blank just for the time being. But the idea is, could you use the input? Could you use n to come up with the output? Could you come up with an algebraic rule? Okay, well, as mentioned, maybe we'll come back to that in a little bit. If you have a good idea, certainly. If you want to pause the video and mull that over for a little bit, that's fine as well. Just one other little pattern that pops up in Pascal's triangle, and this is an interesting one because to some degree it's kind of hidden within Pascal's triangle, is what's called the Fibonacci numbers. Now, we will revisit the Fibonacci numbers on tomorrow's notes worksheet, Perhaps you've seen them before in middle school. There's some interesting applications with the Fibonacci numbers there. But basically, just let me give you a quick rundown of how to get these numbers, and then we'll go ahead and see if we can locate it in Pascal. Again, we will revisit this tomorrow because we're not going to be able to go ahead and write what's called an explicit formula for it. It's tough to write this in terms of n, so what we're going to do is find an alternative way to pull that off. Anyway, you do start out with 1, so 1 and then 1, and then this number is very simply achieved by adding the previous 2. So the 3 is achieved by adding the previous 2. 2 plus 3 is 5. 3 plus 5 is 8. So it's always the sum of the previous 2 in order to get the next one. So if I wanted the number after the dot to dot here, add those two up, and there's my next one. So I just figured I'd show it to you in Pascal's because, again, it's sort of hidden, the 1, 1, 2, 3, 5, etc., etc. But you can just kind of peek up here, and then we'll get moving on this piece in just a minute. So I'm going to do it dotted just so you can see. But I'm going to go ahead and try to keep these parallel as best as possible. Don't know if I did my job already, but let's see. So there's 1. There's 1. There we go. That's a little better. I think I can get it on this. There's 2. There's your 1 and 1 making 2. There's your 3 right here. 1 and 2 making 3. Next one is 5. There it is. 1, 3, and 1 making 5. Next one is 8. And again, these, if I drew my nice triangle correctly here, and if I sort of drew my lines perfectly, they would be parallel, by the way. Tough to kind of tell up there. But anyway, what am I at? 5. And then this would be, here's the 1, 4, and 3. There's 8. How about one more for good measure? 1, 5, 6, and 1. There's your 13. And what the heck? I'm just sort of looking at this piece. How about this? How about 21? 1, 6, 10, and 4. There's your 21. And this obviously keeps going and going and going. So it's just kind of interesting that it is hidden within Pascal's triangle there. Again, we're not going to write an algebraic rule for it today. We will do that on tomorrow's notes worksheet. All right, well, let's get moving on some more formal stuff there. As I said, just introduction of Pascal's triangle is just helpful to talk just about patterns, and because we will see Pascal's triangle again. All right, well, let's get formal, as I mentioned. So a sequence, what we're going to focus a good portion of our attention on this unit. By the way, it's a function, and in fact, I've already talked about inputs and outputs. So it is a function, slight difference from all the other functions we've seen this year. The domain is going to be the set of positive integers. So you will see the inputs being 1, 2, 3, 4, 5, etc., etc. there. This is what is called a discrete function, not a continuous function, and that's what we've been spending most of our time on this year, is continuous functions. So this is going to be in a slightly different context of discussion. Some notation that you're going to have to get used to here, obviously, so let's kind of talk about that piece. Let's see what I have. So really it's inputs and outputs, as I mentioned. The inputs will represent the term number, and really we're going to start out with term number 1, term number 2, term number 3, etc., etc., etc. And what we have is our independent variable. Our generic independent variable for sequences typically is n as opposed to x. So the nth term, you'll hear me talk a lot about that over the next several days. The nth term. Give me a formula for the nth term in this sequence. Now the value of our particular term is going to be the outputs. And so this would be the value of the first term. We would read that as a sub 1. The value of the second term, a sub 2. Value of the third term, value of the fourth term, value of the fifth term, dot, dot, dot this. And so what we're going to do is write formulas for the value of the nth term. So you're going to see a lot of a sub n equals. And that's going to be our situation. So instead of y equals, that kind of generic dependent variable, it's going to be a sub n equals. Outputs in terms of input. Wonderful. All right, well, I'm going to move right on to the next piece. Now there are two types of formulas that we're going to explore over the next couple days here. And so the first one, if you get an opportunity, you might want to just go ahead and underline it, is what is called an explicit formula. In fact, we already wrote one, that one with the sum of the numbers in Pascal's row. That was what is called an explicit formula. And very simply, an explicit formula is an equation for the nth term. Always in terms of the input. So when we talk about this, explicit is in terms of the input. Now the second type of formula, which we're going to see tomorrow, is actually not in terms of the input, but in terms of outputs, and that's going to be a little different. But in the time being here, so explicit is in terms of n, in terms of the input. And so we'll start it out nice and easy. I just have a few examples to sort of get us thinking in the right direction here as to what I'm looking for. In this case, I have the formula. What would be the values in this numerical pattern as a result? So here's how we're going to play it out, everybody. This is the formula right here. Output in terms of the input. And so if I'm looking for the value of the first term, that very simply means the input is 1. If I'm looking for the value of the second term, very simply that means the input is 2, right up the line there. And so when you get an opportunity, let's just go ahead and get used to this piece. So 1 goes in, 1/2 comes out. 2 goes in. Again, this is just the mathematical rule telling us what to do to the input to get the output. And if I want the value of the second term, well, 2 is the input. So that, and you get 2/3. Do a couple more here, just kind of thinking out loud with this. 3, and you could probably pull this off on your own. I would just write it down and get comfortable with the aspect behind it, but really not too bad. So a sub 4. The nice thing about explicit formulas, of course, working mathematically, I'm going to go ahead and dot, 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 because I see it wants the 10th term. I don't need 5 through 9 in order to get the 10th term here. All I need to do is know that 10 is the input, and that would be able to give me the output. So kind of one of the advantages to explicit formula, as we'll see, and we'll contrast it with what's tomorrow. So anyway, just sort of thinking about this, how about 1/2, 2/3, 3/4, 4/5, dot, 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 10/11. If I asked you for the value of any term, yeah, you can get it. If you have the formula, of course, you can certainly get it. And so our values, input to output, input is 1, output is 1/2. Input is 2, output is 2/3, etc., etc. From one to the next to the next. Not continuity there. All right. Well, how about you guys take letter B for me? If you don't mind, pause that video for just a second. And, well, I'm going to have to do this one as well. I don't have it on my paper. But let's go ahead and pull this off, I suppose, together then. So this would just be 2 times 3 to the first, 2 times 3 to the second, 2 times 3 to the third, 2 times 3 to the fourth, and dot, dot, dot. I'll have to come up here, 10th term, and 2 times 3 to the 10th. So just kind of looking at this piece, it looks like the first value in our term would be 6. Next one would be 18. Next one there looks to be 54. And let's see, next one there, I got 162. Sorry about that. Balked on that for just a sec. And then that last one might need a little assistance on. So let me just go ahead and grab my calculator and pull this off quickly. But you can see, obviously, pretty straightforward. 2 times 3 raised to the 10th. And you get that right there, 118,098. All right, so 118,098. Nice. So 2 different explicit formulas there. If I asked you for any value in its sequence, you can certainly give it to me. Okay. Let's go ahead and see if we can now switch gears a little. What if I give you the numbers? Would you have a way to go ahead and pull this off? And by the way, just sort of looking at my A through D here, everyone see the letter D? There are your triangulars again. So in this case, I'll sort of give it to you. Now, I'm going to rewrite those numbers there because I want to play around with it just a little bit. So I have a 2, 5, 10, 17, 26 there. And again, I'm trying to find a rule to go from inputs to outputs. Okay, so think about it for a minute. It'd be great for you to pause the video on occasion. These are your inputs, and I need a mathematical rule to translate those inputs into these outputs right here. So those are our n values, and what I'm looking for is a way to get the value of the nth term based on n. And so in this particular case, just curious what you see. How do you make 1 go to 2, or 2 to 5, or 3 to 10, or 4 to 17, 5 to 25? Especially these, they kind of strike me, it's really close if you look to the squares, aren't they? You know, 4 squared is 16, 5 squared is 25, and then I start going backward. Oh, wait a minute, 3 squared is 9, 2 squared is 5, I'm sorry, 2 squared is 4, 1 squared is 1. So again, it's tough kind of talking to a board with this one rather than an entire class and getting feedback. But I guess what you're looking for is just anything you can do to those inputs to get the outputs. And I see it as you want to square those inputs. That'll get you most of the way there. And then maybe just it looks like it's +1. So maybe you came up with that piece as well. Maybe not, and that's quite all right. But essentially, that seems to be our algebraic rule. So as I said, if I want the 10th term, 10 squared plus 1. If I want the 20th term in this pattern, 20 squared plus 1, et cetera, et cetera. Okay. Now, this one is one that we're going to definitely see coming up. So I'm curious about what you catch here. I'm going to go ahead and just rewrite same thing, 1, 2, 3, 4, and 5. And I'm looking 1, 3, 5, 7, 9. All right, so it'd be great if you pause the video. Love for you to see if you can pull this off on your own. But come up with a nice algebraic rule here. So, you know, and actually this, as I said, is one of the patterns that we are going to do a lot of work on. So let's see if we can introduce. It looks like if I asked you for the next term and the next term, you would probably know exactly what to do. It looks like I'm adding 2. So, and think about this, just good old-fashioned mathematics here. It looks like I am repeatedly adding 2. Well, repeated addition actually is a particular one of the primary 4 operations. Repeated addition is multiplication. So if I'm repeatedly adding 2, something tells me it has to be a 2 times our input. So because repeated addition is multiplication. And so as a result here, well, let's see. 2 times 1 obviously is not 1. 2 times 2 is not 3. 2 times 3 is not 5. 2 times 4, etc. But I'm pretty close. After I multiply it by 2, do we have a firm rule to get us back to these outputs right here? Well, 2 times 5 is 10. How about -1? And I think that's going to work if you kind of look at it. But just sort of understanding, all right, well, what does that mean mathematically? And then can we translate it algebraically? And this is linear, as a matter of fact. It has a different type of name that we're going to look at. But for right now, it's increasing by the same amount. Okay, let's go ahead and try the next one. So I'm going to do 1, 2, 3, 4, and 5. Looks like I'm going to do this as 1 over 1, 1 over 2, 1 over 4, 1 over 8, and 1 over 16. Interesting. So a couple things that jump out at me, first of all, is I go ahead and write this. So a sub n equals, and it looks like the top is always 1. I don't know, just kind of thinking maybe we want to just do a 1 over. It looks like no matter what, that's a constant. Now the denominator is sort of the issue at hand here, and these look like they're going, well, I would be multiplying by 2. And repeated multiplication, as we know, is an exponent. And as you can see, these numbers seem to be powers of 2. Unfortunately, though, this is 2 to the 0. This is 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. So it looks like I'm a little out of sync. So I'm going to do it wrong, and I'd ask you to fix it. It's not 2 to the n. What do I have to do to those inputs first before raising it to the power. So it looks like this is 2 to the 0. So what do I have to do to the 1 to get to 0? I'm seeing that. And as a matter of fact, this type of expression will come up in just a couple days. But yeah, I think that's going to be the case because this is 2 to the 4th down below, even though we're at term 5. So I would take 5 minus 1 first, then 2 to the 5 minus 1. All right, very good. Let's go get those triangulars. See if you came up with it. And again, if not, no worries at all. A lot of students are able to kind of look at this and know exactly what to get next and next and next. But to translate that explicitly is not easy at all. So I tried to give you a little hint there. You actually need 2 different inputs to sort of get that output there. So what do you do to the 1 and the 2 to get 1? 2 and 3 to get 3. 3 and 4 to get 6. 4 and 5 to get 10. 5 and 6 to get 15. And so, as a matter of fact, you do this. You take the input, which is n, and you multiply it by the next input. So I have to do 1 times 2. This input times the next input. And you want to know how algebraically to represent the next input if our current input is n? How about n plus 1? So I would do n and then n plus 1 and then divide it by 2. It happens to be quadratic if you sort of look at it. And that would be sort of the situation here, but that would be our nice little algebraic rule. So if this is my n, 5 is my n, 5 plus 1 is 6, 5 times 6 is 30, divided by 2 is 15. And that's the algebraic rule for your triangulars. Okay, very cool. So just one last item on the agenda there. First of all, let me box these up, and you can certainly do what you need to do on your notes worksheet. And so there's one last symbol that we're going to do some work with over the next several weeks before the end of the year, and it's what's called a factorial. So this is going to be the symbol that we're going to look at, this exclamation point. And we'll go ahead and just kind of define it. As it says, factorials defined for non-negative integers. Factorials can be defined beyond this, but for our purposes, it'll only be for non-negative integers, meaning 0, 1, 2, 3, etc., etc. So a couple things. It says are defined as. A couple are sort of given. So first and foremost, 0 factorial actually is defined as 1. And I'll kind of try to show you sort of why that is. I'll give you a quick explanation for that piece, because that one is a little counterintuitive, although mathematically it does bear out. And for all the work that we're going to do with factorials, this does have to be the case in order for that to fit. So 0 factorial is defined as 1. 1 factorial is also defined as 1. And then here's where it gets interesting. What we're going to look at is any non-negative integer as a factorial. And so n factorial would be that number times the previous integer, times the previous integer, etc., all the way down until you get to 1. So jot that on down there. And then I have a little example, as you can see on your paper. So it says, for example, 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. And so that value, and again, we'll kind of work on the calculator piece momentarily here. But yeah, you can see exactly that. So n factorial is just that number times each integer below it all the way down to 1. Okay, now we're going to look at a little factorial growth momentarily here before doing example 3. And then we'll go ahead and kind of, yeah, I think we'll kind of do that piece. So one thing first, this always comes up. Students always ask, because based on this, it looks like, hey, wait a minute, what's going on with that 0 factorial? So let me at least try to give you a quick explanation. And you don't have to write this down, so you can just kind of peek up at the screen here. So let me just start a little ahead of the 0. So if I asked you for 3 factorial, you would tell me it's 3 times 2 times 1. 6, of course, right? Well, another way to describe that is that it's going to be 3 times 2 factorial. So 3 times 2 times 1 is really 3 times, well, 2 times 1 is 2 factorial. Which means, of course, 2 factorial is really the same thing as saying 2 times 1 factorial, right? 2 times 1, and 1 factorial is 1. Hope everyone's okay with that piece. Now, following the same line of reasoning, what that should mean for us then is 1 factorial. Sorry, let me do that a little better here. That 1 factorial is going to be 1 times 0 factorial. Everyone okay with that line of reasoning? Just following the pattern, it's the number times the previous factorial. And then, of course, if I solve for this, you see that 0 factorial is 1 factorial over 1, which of course is 1. So again, just a quick little numerical trick. But basically, 0 factorial is defined by 1, and maybe you can see how this pattern kind of fits exactly that definition. Okay. Well, here's what's kind of interesting about this. Factorial growth is staggering. We talked about exponential growth being impressive, things that double really increase immensely fast, but exponential growth has nothing on factorial growth. So let's just do a couple. We have a little time here, so let's pull it off. So let's find it on the calculator. Let's do something simple, like how about 10 factorial? So everyone hit the number 10 if you would, and then go under Math, and you're going to move it over to this one right here, guys, the PRB. I'm just going to go one to the left, and actually this is a menu that we will do a little work with. These two things in particular we're going to see in a week or two. But for right now, you see obviously there's the exclamation point, so I'm going to go ahead and get that. And think about this for a sec. 10 factorial. Seems pretty harmless, right? 10 times 9 times 8 times 7 times 6, right down the line here. And just that alone, 10 factorial, if you notice, is over 3 million. Just 10 times 9 times 8 times 7, right down the line. Try this one. How about something like this? Now just bump it up by 10. Let's do 20 factorial. And you could see how incredibly large these numbers get in a hurry. So this, guys, is 2.4 times 10 to the 18th. Huge, huge, huge. You could start, I forget where it is, where's the overflow? And the overflow, by the way, would be at, excuse me, just kind of thinking about this piece for a sec. The overflow would be at past 10 to the 100th. So if I remember correctly, it's somewhere around there. So, oh, okay. So 68 factorial was this times 10 to the 96. So what that means is move that decimal place 96 places to the right there. Let's just see. I'm curious where the overflow is. Is it 69 or is it 70? Let's find out. So just kind of looking at that. Oh, we got 69 factorial in. Let's see if 70 factorial will work. And there it is. It overflows. So 70 factorial, just 70 times 69 times 68 all the way down, is a number that has 100 zeros, basically. Awesome. Okay. So now you know where that factorial thing is. Here's what I'd have you do if you get an opportunity. This one's pretty straightforward. Same idea. List the first 4 in the 10th. So the first term, put 1 in. Second term, put 2 in, etc., etc. I'm going to give you my answers here. I'm hoping I have this on my sheet, and then we'll kind of round this out here. So I believe a sub 1 is 1. A sub 2 is 1/2. A sub 3 I get as 2/3. A sub 4 I get as 3/2. And you can see sort of it's a ratio of factorial growth to quadratic growth. And you can see initially it's pretty close. Even just by getting to the 10th term, though, you could see that the factorial growth far outpaces the quadratic. So that would be the 10th. So this would be 1, 2, 3, 4. This would be your 10th. Okay, so just getting a little practice dealing with representing algebraic patterns. And if you have some questions, you'll let me know. Thanks for listening, of course.